So guys, now let's go ahead and discuss about the geometric intuition behind the principal component analysis. Now, obviously, you know that principal component analysis is used for dimensionality reduction, right? Dimensionality reduction. That basically means we are going to extract some features with respect to the older features that are present in the data set. Let's say I have features like size of the house and number of rooms, and this is basically the price of the house, which is my output feature, right? This is my output feature. Now here, let's go ahead and probably plot a data points between the size of the house and the price of the house. So let's go ahead and plot some data points over here. And let's say this is my size of the house and this is basically my number of rooms. Now, let's say that I have some data points which looks like this, right? Let's say I have some data points which looks clearly like this, okay? Now, in this particular case, you can see that from this, you are able to find out when the size of the house increases, the number of rooms are also basically increasing. And obviously, it is a common sense question. It really needs to increase. When the size of the house increases, you can assume that, yes, the number of rooms is also going to increase. Now, let's consider that with the help of PCA, okay, I want to reduce this 2 dimension of features into 1 dimension, okay, into 1 dimension. Now, if I want to perform this, that basically means I just want to convert this 2 dimension into 1 dimension, okay. This is what I'm actually looking with the help of PCA. That basically means instead of having 2 independent features, I just need to have 1 independent feature and try to basically create that independent feature, try to find out this 1 dimension or independent feature. Now, in this particular scenario, let's say that one way, obviously, I've already taught you, right? Feature selection. In feature selection, what you can do, you can take either one of the feature and you can ignore the other feature. And a simple way of converting a 2 dimension into 1 dimension is that what I will do over here is that I will make sure that I will plot all this point in my x-axis. Let's say I'm just going to project all this point in my x-axis. So here you will be able to see here I'm getting the point, here I'm getting the point, here I'm getting the point, right? So once I do this, you'll be able to see that I will be able to project all the points over here. Now, when I project all the points, obviously I'm able to get all my data points in 1 dimension. So this data points that you'll be seeing, we are able to get it in 1 dimension. So here what I have done, I have basically converted this into from 2D to 1D, right? And one more thing with respect to this specific data points, which is super important to understand in PCA is that if I probably see the first data point and the last data point, the area between this is basically my spread of the data points. Now, if my spread is huge, then what will happen? My variance will also increase. My variance will also increase. If my spread is increasing, my variance will also increase. Okay, so this is both are directly proportional to each other. Now, what is the disadvantage by using this approach where I'm directly projecting in my x-axis? So here, obviously, the size information is getting captured, but the number of rooms information is getting lost. So this information that you had related to number of rooms, why this information is getting lost? Because understand over here, if I try to project from here to the first point also, right? Here also you have some amount of spread. Now, as I said, if the spread is increasing, the variance is also increasing. And over here, because of this variance, here also some information regarding number of rooms are there, right? And you're directly skipping this information. You are neglecting this information when you use this specific approach, right? Wherein you're directly projecting into 1 axis. So here with this approach, what is the major thing that is happening? There is loss of information, right? And in this case, you are losing the information about the number of rooms. Obviously, you created from a 2 dimension, you created a 1 dimension, and this is all your 1 dimension points. But from this, when you convert it from this 2D to 1D, you are losing much information from the number of rooms, right? About one specific feature. Now, because of this, what will happen? Once you lose all this information, your model may not perform well with respect to this specific predictions. So here, in short, you're doing feature extraction, but you're doing feature extraction with a lot of information that are lost, right? So in this feature extraction process, you're losing a lot amount of information, right? So So I hope you have got this specific idea. Now, you also have to take care when you do this kind of feature extraction, this information need not be lost that much. So how do you prevent it? So in PCA, to give you a brief idea, let me draw this particular diagram again. Let's say if this is my size and this is my number of rooms. And let's say these are my data points over here. Let's say these are my data points over here. Now in PCA, what you do is that you do some kind of transformation on this axis, on this x-axis and y-axis. What kind of transformation? You apply some mathematical equation. I'll again not talk about that mathematical equation right now, but I'll just name it. You apply something called as eigen decomposition on some matrix, Okay, we'll discuss about this, what exactly this is. But in short, you're going to apply some transformation, and this is this specific transformation. And with the help of this specific transformation, you will be getting a new axis which will look like this. Let's say this will be a new axis which will look like this. Okay. And once you get this specific axis, what will happen is that then you will try to project this information over here. You will try to project all this information over here. Now, when you try to project this specific information, okay. Now, suppose since you have two features, you will try to apply some transformation which will change this size axis to some other axis like size dash, and one more axis will get created. Let's say the other axis will be exactly perpendicular to this axis, okay, and this will be your number of rooms dash, and then you will be projecting all these points over here. So when you project all these points over here, here are your data points. Now in this projection and in this projection, what are the differences? In the previous projection and in this projection, what are the differences? Now see, in the x-axis, if I consider this as my new x-axis, here you'll be able to see that the spread is properly captured with respect to the specific points. And similarly, if I try to plot all this point on this new axis, here you'll be able to see your spread that is going to get lost once we project over here will be very, very less. So here, what you're doing is that you are applying some transformation and you're creating a new axis like this size dash and number of room dash. And once you create this new axis, all you do is that you now just project all this point to this particular axis. And after projecting this point, you can see that maximum variance is getting captured for all the points over here. So here, maximum variance is getting captured. And why this is better than this? Because in the y-axis, you're not losing much information. You're just losing this amount of information, right? This amount of variance you are basically losing, right? When you project it on the x-axis. Now with this transformation, you're able to convert your 2 dimension into 1 dimension, and you're making sure that much information is not lost. And how do you come up with this specific point? Because see, in the y-axis, because of this new dimension, here the variance is less, right? So even though you project this point over here, most of the variance is basically getting captured by your x-axis. So much information is not lost. If you compare the previous example here, once you project it into the x-axis, huge amount of information is getting lost because here the variance is quite high or spread is quite high. Here it is not that high, right? So I hope you have understood. Our main aim in PCA is that to find out this kind of lines, right? So after transformation, which is the new axis that is basically getting created. Now, since I just had 2 dimensions, so after I do the transformation, I basically call this as principal component analysis 1. So PCA 1, principal component 1, and we basically say this as principal component 2. Suppose if you have 3 dimension, that basically means you will be having three principal components. Always remember PC1 will be capturing the maximum amount of variance, and then PC2 will be capturing the next maximum amount of variance. Similarly, if you have three dimension, then PC3 will be capturing the maximum amount of variation after PC1, sorry, maximum amount of variance after PC1 and PC2, right? So over here, in geometric intuition behind PCA, our main aim is to basically find out principal components, right? Like how we find out this. And at the end of the day, we really need to find out one line that should be able to capture maximum amount of variance. And once we take this PC1, and then we can convert this into from a two dimension, we will just be taking up this specific point and it will finally get converted into a one dimension point, right? So I hope you got an idea about what is the geometric intuition behind PCA, that is principal component analysis. We'll talk more about what is eigen decomposition on metrics and what is this specific transformation. With examples, I'll try to show you, but just understand that your main aim is to find out the principal component which has, after projecting all the points, it should have captured the maximum variance or spread. Okay. And why variance is important? Because variance basically talks about the data, how the data is basically spread. And with the help of variance, you'll be able to capture more and more information. So guys, the final goal of a PCA algorithm will be that to find out the principal components in such a way that maximum variance will be captured. So suppose if I have two dimension points, then I will basically be having PC1, then PC2, right? And we know that the variance with respect to PC1, after we project all the points in that particular component, will be greater than the variance with respect to the principal component 2 once we project it. Suppose if we have specifically three dimensions, then here you will be able to see that we will be getting three principal components. Okay, that basically means like we'll be having three different axes. One is PC1, PC2, PC3, and obviously the variance with respect to PC1 will be greater than the variance with respect to PC2 after we project the points, and the variance with greater than PC3. Okay, so this variance will be following this specific approach. So let's say that if I have a task wherein I have two dimension points, which is like this, and let's say I want to convert this 2D to 1D. So at the end of the day, what I will be doing is that the PC algorithm will be finding out the best principal component line. It can be this line, 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 and it will try to select the two best principal component lines. And how we say that this is the best principal components line? Because once we project, let's say once we project this specific points on this line, right, we will be able to call this line as the best line only when the variance that is getting captured is maximum. Okay, so let's say this line has actually captured the maximum variance. So I will say this as PC1. Suppose if this line has captured the second maximum variance, then I will basically say it as PC2. So this specific line will be my PC2, right? And at the end of the day, if I'm converting this into 2D to 1D, then what will happen? I will basically be taking up all these specific points that I have actually plotted over here. Okay. So guys, the final goal will basically be to get the best principal component. And how do we say that it is the best principal component? Which captures maximum variance, right? Which captures maximum variance. Okay. Now let's say that if I want to convert a three dimension point to one dimension. Now in the case of three dimension points, we will be getting three components. One is PC1, PC2 and PC3, right? And obviously it can be all these three lines, any of the best three lines. And you know that the variance of PC1 will be greater than variance of PC2 and this will be greater than variance of PC3. So since I really want to convert this into one dimension, what I will do, I will project all the points in PC1 and I will be taking all these points as my one dimension point, right? One dimension point. Let's say if I want to convert this 3 dimension into 2 dimension, then what I'll do, I will probably take PC1 and I'll also make sure that I'll project all the points in PC2 and I'll take this 2 information and combine it together to basically get my 2 dimension, right? So this is what is the approach that we are going to follow. Again, let me repeat it. The major and the final aim of the principal component analysis is to find the best line after the transformation, which will be able to capture maximum variance. And the line can be existing anywhere in this space, right? And with respect to that, based on the number of dimensions that you want to convert, you can take that many number of principal components, okay? So yes, in the next video, we are going to see the mathematical intuition behind how this transformation basically happens. And that is where we are going to learn about eigen decomposition on a specific matrix. We'll talk about what are the steps and how do you project it. We will also see that how do you project the specific point on the specific line and how do we make sure that the variance will be maximum. We'll be discussing about that, okay?